Okay, so before we get into looking at longitudinal and lateral directional control specifically, we're just going to take a quick review of feedback control in general. So first of all, let's just revise what our primary controls are of our aircraft and what they do. So in the longitudinal sense, we have the elevators and we have the throttle as well. And in the lateral directional sense, we have the ailerons and rudder. So what a pilot can do to maintain or to change a particular flight condition to another is to apply either the longitudinal or the lateral directional controls, or a combination of both, and then basically monitor what happens, right? So it's all about obtaining a new flight condition or maintaining a given flight condition, right? And there's different ways of assessing whether your control input was successful or not, right? And this boils down to what's known as both open loop and closed loop systems. So an open loop system will rely on the pilot themselves to evaluate the output having made a control input, right? So we're going to talk about this a bit more specifically in a moment, but essentially the pilot would manipulate the controls, monitor or assess or somehow measure using the instruments how the aircraft has reacted to that control input, and then analyze and make decisions on whether those control inputs were successful or not for the desired flight condition, right? So that requires a constant reassessment of this open loop system where the pilot themselves has to make these judgments. Well, for a closed loop system, these adjustments are made automatically by a flight control system, for example, flight data computer providing calculations to control actuators and that kind of thing, right? So in this case, a control input is made, and then sensors are used to measure or monitor the output, and then automatic adjustments are made to actuators on the control surfaces to constantly reevaluate the flight condition that's been obtained, right? So typically closed loop systems have been used to aid stability. Remember our discussion about the yaw damper and how angles of side slip or perturbations in side slip angle are damped out by an actuator on the rudder. That's an example of how closed loop systems can be used to aid stability. Also, you might think about fighter aircraft or aircraft that are designed to be highly maneuverable, where, for example, control inputs are amplified automatically to aid handling or to give the aircraft better maneuverability in terms of the control forces, the control manipulation within the cockpit, right? So those are the two different types of systems that are at play here, and we also need to consider the four different types of response that our aircraft may have to those control inputs. So here I have four different types of control input. The first of which is an impulse, so it's a short, sharp impulse and then back to the original position of a control surface. The second one is a step input, so the control surface position has been changed and then it's maintained. The third one is some kind of oscillation or sinusoidal input of the controls at a particular frequency f. And then the fourth one is noise, basically, perturbations or turbulence, if you want to think of it like that, right? So in this first case, Remember our discussion about the short period pitching oscillation? Well, this is the control impulse that disturbs or excites that particular mode in the longitudinal sense, right? So we have a control input, so here on this the black axis, C for control input, X for output, right on this y-axis over here in blue. You can see we have this disturbance caused by the impulse of the control surface, and then in this particular case I've drawn the reaction or the output X to be stable, right? And that wants to regain that original trim condition where the control input is back at 0. The second one here is our step input. So we make a step input to our control surface and then maintain it or hold it at that new position, and you can see the disturbance or the output is tending towards, it oscillates, but it tends towards a new condition, right? So that's the main difference between those two, is that obviously the new control input, which is held, wants the aircraft wants to tend to that new condition as imposed by that new control surface position. The third one here, it describes what happens if we make continuous changes of the control input. In this case, I've just drawn the output kind of lagging behind and is slightly damped. And the final one is similar to that, so it's a continuous change in input, but in this case it doesn't follow a set pattern. It's basically noise, it's random, or you can think of it as like the perturbations in alpha or beta during regular flight, which the aircraft has to deal with turbulence and that kind of thing, right? So in this case I've drawn a random control surface input, and then the blue line, which is the output, again slightly lags but is damping out those perturbations. So those are the different types of reaction or response to control surface inputs or control inputs in general. We're now going to have a look at what that means for both longitudinal and lateral directional control.